let's ask the question quite properly. When do we shout at the server? Well, I can't reproduce an issue, right? Something happened and it went wrong, and I can't get it to happen again. The code's the same, the build's the same, maybe even we've like started over again and repushed the code. It's exactly the same, the workload's the same, measuring network traffic's the same, and for some reason, I can't get whatever went wrong in that one run that was really interesting. I can't reproduce that issue. Different than like trying to reproduce something from production, because we know production can be really dirty, crazy data and really crazy workloads and things like that. In a test lab environment where it's like, look, this is pristine, exactly the same kind of traffic, and I think it's exactly, but for some reason something is different and I can't reproduce the issue, I will shout at the server. If an issue appears random, completely randomly shows up, intermittent, things are running all of this running the load test, and it sort of happens and it sort of doesn't happen. And then when it happens like 3 times in a row. So it looks like it's repeatable, and then it doesn't happen again. And you're like, what am I missing, right? I'm doing all the things right. I've got code in my head. I'm a good performance person, so I'm measuring my CPU, my disk, my network. I'm measuring all the application stats and all this I'm learning from going to all the various Neotys packs over the years, and I'm applying all those good practices. And I'm doing all that, and I still can't get something that just appears to just happen completely. I cannot explain it unrandom. I'm going to go shout at the server. If I have really weird sort of low-level exceptions coming out of system calls, maybe the operating system itself, if you're looking at something that doesn't actually have a complete code. And one of the things I'll find is that there's things where you'll find a low-level exception, and you go look like, show me everything for Red Hat on that. Show me everything in the Windows environment. Show me everything. And I can't find in any of the knowledge base articles anything that refers to the code that I'm finding, or there should be a code and I'm not seeing a code. So like something happened way down in the system level and it's not giving me the information. I will go shout at the server. There's a good one. I don't know what happened. It was working fine. And I just give up and I go shout at the server. By the way, that is a picture of Nikki Sixx, I believe, with a baseball bat that would do a lot more than just shout at the server. If you've ever been running massive load tests and you're like, look, something just stops working absolutely and completely, the server just shut off. It won't come back on. Then I'm instantly into we've got some issues going on and start shouting at it. Here's the other thing. That same workload works exactly fine on this other server. And this server looks like it's running, but it will not run that load. I even opened up the box, looked at every component, looked at the model numbers, looked at everything except for the series. Every component is exactly off the manufacturer's shelf, but that one works and that one doesn't. I am going to start shouting at the server. So the lesson I'm wanting to share with you, which may seem irrelevant to the cloud-based world, listening to Gorenka's talk and others actually earlier today, their hardware is still a real thing. That VM you're running, somewhere in the world is running on a piece of hardware. Memory is memory. It's physical, right? Memory is memory, CPU, power is power, cooling. It's just maybe somewhere else in the world, and it can still affect your application. But typically what I find, and this is recently, I currently work with a hybrid model on a couple different applications. Some run totally on-premise. Some have compliance issues and data location issues. We have to run them physically in certain places, and we do that. And we have some other stuff that runs in a mix of Azure and other cloud situations. So I've actually been doing a lot of work recently with some really awesome, super fast storage, some really cool on-premise kind of old school data center kind of stuff. And I can tell you generally, if this is sort of new working in the hardware world for you, just to give you the basics of what I've dealt with in the last 3 years, what causes a component to fail. And, if you've ever blown up your home PC that you've spent, a couple $1,000 on all this stuff, put it together, and then it runs for 6 months, and then one day it's got that weird smell and it blew up. Yeah, voltage and electricity, right? And there's two different kinds of electrical things that generally affect a compute system or a microprocessor-based computing system. One is voltage variations, and that means you've got voltage surges, so increases in variation, increases in, or brownouts, which is sort of a decrease in surge in voltage. So voltage variation, and of course, in all of the computing systems that the majority of us work, everything is converted into direct current when they're running on in your component systems, and there's a bunch of voltage regulators that are supposed to do their job. They stay within a very specific tolerance. So electrical things, you try to have layers and layers of things to make sure that power is incredibly clean before it actually comes in to the sensitive parts of the system itself. The other thing is, obviously, electricity is required to run your computer, and so upstream current failure, meaning it's not really brownout as much as it in terms of the components failing along the chain locally. But if the UPS you have starts flaking out and getting weird, the transformers themselves outside the lab, and then, of course, the source that you're running, but any of those variations, that upstream current, not necessarily in my computer or the server, but from the components and the data and the electricity that's coming. So electricity will cause your components to fail. The other major thing is heat, and of course that's related if you know anything about resistance within a circuitry and the way electricity moves along a substrate of some kind. That could be a metal of some kind, a conductor of substrate. So as you have really low resistance, you can move a tremendous amount of current and have very low heat. And of course, that's the innovations you see as we invent substrates that can have very much lower resistance and lower heat. Then we can start running things faster and faster. And as you know, compute speeds keep getting faster and faster. With a limited return, now we're into, well, now I think we need to get into this parallelism thing. Like, what are those OS schedulers that we're talking about? Okay, cool. So heat, it has very specific, it'll kill things. Basically, if you really think about heat, it's really good at melting things. I was watching the new Justice League, and there's a whole bunch of stuff about these, like the 3 cubes. Remember the 3 cubes thing in that movie? And he like uses a laser and is like, it's the hottest thing on earth. Again, that's a reference to Justin Bieber, apparently, in the cache servers in Gorenka's talk. But melting things, heat is really good for melting things, and computers don't like to be melted. And I'll talk about that. There's also just absolute heat limits, not in terms of variation. So you have something that when it's warm, it expands, and when it's cold, it contracts. So the idea that you have the components of a system that have to stay within a very specific space, but they're constantly expanding and contracting and expanding, contracting. You know, if you've ever taken a paper clip and bent it one way and never bent it again, it'll stay pretty strong. But if you bend and bend and bend and bend and bend, it'll break. So that's the same thing that can happen metallurgically in the constructs of the contacts, the actual substrate that's used to conduct electricity down a circuit. The absolute heat limits are just straight up, I don't have enough cooling, so heat will just build and build and build and build. I'm not removing enough heat from the system, and I reach a critical point where basically it melts. And it could melt either the metal or it could melt everything, the plastics, all the other different qualities and different hardnesses of plastics at different times and tolerances. And I for one, have actually melted a motherboard. It was a Sun server. It was a Mule box at Microsoft, but running a TPC benchmark on a SQL server. And it actually melted the entire thing. That was really nice. The other thing, and this is something actually I learned more so from Gorenka a few years ago, and then following up some people at Intel that I know, physical malformation. And that, I mean, is just manufacturing defects, right? So the anomalies with manufacturing, and of course the inaccuracies that come from that. So you'll have sort of first bin or first pick, meaning the best quality stuff that came off the assembly line, the supply chain. And then there's second bin, third bin, fourth bin. So if you've ever bought really cheap electronics, you can buy cheap electronic components because they actually came off the line with a few they weren't quite as tolerant to heat. They weren't quite, and they do all the testing of those things. This one goes, this is good, oh, here's a bad one, throw it in this other bin. and then instead of being $200, it's $100, it'll still work. So there's all kinds of things in system design for cheap hardware to maximize profit margin so that you can actually take a bunch of really cheap, kind of defective, maybe half defective, partially defective hardware, and still put other components and other designs within how that hardware works to increase retries and basically cheap hardware, because you have to layer on all this logic to tolerate failure, faults. That actually increases the latency with which I couldn't make it to the DIM. I've got to do that again. Well, I'm not going to tell the operating system I did that because you bought cheap hardware. I can fudge all that stuff, and underneath the covers, wow, I can run on really good memory over here in this server, and you put your hand on it. By the way, if you ever get a chance to do this, it's really fun. Put two systems under load, one with cheap memory and one with really good memory. Same speeds, same specs, but just cheap versus good. First bin versus third bin. And you will feel the heat on that other third server, the cheap memory, will be way hotter than the good memory. And it really comes down to just the quality of the substrates and the components that are used to actually build the chips, the microprocessors, the ICs, everything else. Really interesting stuff. So those are the three things I want to cover as we go down. But let's talk about some myths. And no talk is complete without really going over myths. Here's the myths that everyone wants you to know about hardware. One, components don't fail to operate within the design spec. So if we do all of the math right on paper, and we build a data center on paper, and we do all of the exact T deltas, et cetera, on paper, and we figure out all of those calculations in a computer, but really those are just an electric version of what we're doing on paper. As long as the components are designed perfectly for the first time we build that data center, first time we build that rack, those components will not fail because we're within the maximum heat tolerances. We're in the T delta that we need. We have the exact right voltage coming in, and we have all the mechanisms, secondary and tertiary, to keep that current very clean and very stable. We have enough cooling. We're going to move bits on and off all of the different components, within the tolerances and the rates. We're going to spread everything out. And components don't fail that operate in the design spec is true when you test that specific component to go into the specific bin that you paid for. And then suddenly times get tough and you have to buy from bin 2 or bin 3. And your tolerances for that extra hot, cheap memory blow, and you've got 10,000 servers running in a data center, even a small rack in a small space. Boom, all of a sudden, how come I don't have enough heat? I don't have enough BTUs to actually run all this thing correctly to remove the heat. Really interesting stuff, because your design spec is not just for the component, it's the ecosystem that component lives in. So really interesting. So the first myth is components don't fail to operate in design spec, even if you do get everything right. Murphy's Law. There'll be that one DIM, that one CPU that worked great, and you paid top dollar for it, and guess what? Oops, it had a defect. And it didn't show up in the testing, and you paid top dollar, but it ends up there's variation in this stuff. And the massive amounts of quantities on the supply chain for all of these components means even though it says it operates within this design spec, there are variations within those specs. Here's the other one. Why are we talking about hardware? System level logic handles all those faults magically. And I thought this for many, many years, because I came in from 10,000 feet knowing shit all about components and anything about hardware until I started living in it and talking to people that actually wrote all the drivers. Oh, what do you talk to? I talk to an ASIC microprocessor. Oh, that's like a computer inside a computer inside a computer. And you finally talk to people that write those individual things, and they're like, oh, we don't tell the operating system anything. In fact, we don't even tell the motherboard component we're plugged in. We don't tell them anything about the extra logic we did to handle this fault and that fault, and a retry here and a resend there and a voltage modification here, and then that kind of stuff. Really interesting that you're so far removed from it. You think, well, the system level logic will handle all that, but there are faults and things happening that add latency that an operating system, let alone your application, have no idea that that's the actual source of the latency. These things do add up, especially when they're causing excess heat and power consumption. Here's another one. The upper level application logic is isolated from all that. Your app doesn't run unless there's a CPU. Your app doesn't run unless there's memory. Your app doesn't run, well, maybe there's not disk, but there's probably disk somewhere. And sure, fine, maybe there's no network. But the idea being, even though your application is up here, it's relying on a tower of cards to be lined up just perfectly to run optimally. And don't think that that Jenga tower, you'll pull out that one thing at the bottom and it'll all come down. Oh, here's another one. Expensive hardware is always better. Well, have you ever worked in the sales department doing anything? I mean, if you can sell something cheap as an expensive piece of gear and make a lot of money, a lot of people do that. So expensive hardware isn't always better. It's usually better. But really, you have to, you kind of got to game the system. You got to get ahead of the Facebooks of the world who have already paid and put millions and millions on the table to get the first run of a given set of chips and things like that. The infrastructure team will fix that before we go live. Oh, if there's any hardware issues or hardware faults, the infrastructure team will, well, if you go to the infrastructure team and say, hey, do you guys already know the things that are going to go wrong? And then they're like, no, we react to shit that goes wrong when it goes wrong in production. We don't know before it goes wrong. We don't know that that disk is going to fail. Sure, we maybe do some tests. Sure, maybe we can be kind of proactive, but doing a disk or a memory test is not the same as an actual application over the long haul of 72 hours at 99% hammering memory operations. So yeah, the infrastructure team is just trying to stay alive and keep these things running. The other stuff that I witness is all of our stuff is running virtual, so it's not an issue. Oh, sure. Well, I don't know about you, but a hypervisor, any kind of control plane that sits and abstracts you from the hardware, the operating system, of course, already does this for you. But guess what? That's software. That's your application talks to a bunch of other applications that talks into a layer of a bunch of other applications that talk into a hypervisor that, guess what? It's still just software. There isn't magic within the virtualization layer. There's some nice features where all of a sudden some host starts to, whoa, this is getting unstable, and it'll automatically fail over or move your workloads to other servers. Brilliant. But that doesn't mean it's not an issue. That's an issue because, believe me, if you start having a domino effect failure going across a huge cluster, suddenly there's nowhere to move. There's no healthy node in the entire cluster. Wow, we really got the sizing completely wrong, right? We got all of these selections wrong, and it can create a domino effect. Really interesting stuff. But Mark, we're running in the cloud. I don't even have hardware. Can't even touch it. And I'm like, that's right. You're absolutely right. We don't control or own the hardware. We don't have access to monitor the hardware. I don't know what switch or what fabric I'm connected to for a SAN. I don't know how many miles of cables are back. You're right. We don't even know if we think something's wrong from the old people who remember what hardware is. Yeah, who would you call? Like, how would you know? How would you get to somebody that says, hey, could you? No, for legal reasons, I'm not allowed to disclose to you anything about this. If you've looked at the outage reports or the nice things they try to share with you, apparently one of the data centers had an issue. Whoa, that's a laundry list of things, of thinking and decisions and really pressures to be profitable. At this point, cloud models, and this would be a great conversation with Gorenka, is the business of these cloud models, right? And we know how to operate a room full of hardware and make money. Well, some people are squeezing. Certain ranges of cloud providers are squeezing to make money out of every CPU tick that they can get. So we wouldn't even know who to call, and they're probably not going to tell us anything. But we know the cloud, whatever you want to call it, still has massive issues. We hear things going out all the time. Even if our ability to recover from those failures, given the size of some of those failures, is much faster, your application still can run into those issues. A dependency of some kind, a third-party call that goes down. If you don't have, hey, here's my primary web service and I have a secondary and a tertiary, have a plan B. Figure out, hey, whoa, what if our main provider goes down because of some cloud outage? Can we still stay in business? Can our application still work? The cloud providers can be a platform provider, but there's no specific safety net. They don't know about your application. They don't know what you're going to build. They don't know your logic, right? They just like, well, here's some storage. Good luck using it. Great. And here's a bunch of knowledge base and a bunch of forums that people will tell you how to use it. And here's some ins and outs of, wow, did you know about OS level schedulers? Did you know about IO ports, network IO ports, storage IO ports? Hey, how many volumes should I present? And do I have IOPS throttling on that, et cetera, et cetera. But none of that is specific to your application and the performance of your application. You have to learn how that platform performs, and that's it. There's no specific safety net for those outages. I like this phrase, and I picked this up recently. Availability from a platform provider like that is a Boolean over time. It's either on for some amount of time or it's off for some amount of time. And usually, if they're off, you have an argument not to pay them unless you look in the fine print. So really, just being on or off doesn't matter. Being slow, or being slower than you were yesterday, slower than you were before the outage, they don't get into the subtleties of that. Like, well, there was an outage. I mean, come on. Things are just getting back to normal. We're just warming up the sand, et cetera, et cetera. So the availability is a Boolean over time. You really have to look closely at it. It's really on you to be able to compare, hey, something's different after, we get there was an outage, we get there was some issues, whatever. We've come back and we're really consistently 5% lower throughput, and we're still paying about the same amount, potentially. So your apps running in the cloud will absolutely suffer from this kind of latency and stuff, instability due to hardware faults. Let's talk about hardware faults. And again, hopefully there's questions coming in. I'm kind of, I'm in the screen. I'm in the studio screen, so I'm just going to crank through these things. And this is a fairly straightforward, cut and dried kind of talk. And I want to go through my favorites: CPU, disk, memory, network. And we'll start with CPU. And clearly, if you've ever fried a CPU when you try to build your own PC and you forget to, I forgot to plug in the CPU fan. Yeah, you only got like 1 or 2 seconds before that puppy's completely gone. Little bit better later models, but when we first did DIY, yeah, they would just go. So obviously there's an absolute heat limit that you're not allowed to exceed. And a lot of chips, if you look at the overclocking forums for gaming, they're trying to get the fastest polygons per second out of a chip. And that chip could be on a GPU as well as CPU. But the faster you make that chip go, the frequency of the chip, the faster frequency you go, well, you're doing more electrical current on the substrate of the conductors of the circuitry in there, and that resistance is constant. Not really constant. Actually, resistance goes up as with certain. I'm not a physicist and I'm not a metallurgist, but typically you hit a heat wall that says resistance is now infinite and temperature goes exponential. Very interesting. So those heat variations, that's why you see them on things, are controlled by your fans and also by throttling. So some of the nice safety features in some of the microprocessors are, hey, if I detect that somebody's stuck me into a situation with bad cooling, not enough cool air, not enough heat removal, basically, or I was running fine and then the AC went out in the room, now I have to survive running for a little while with hot air coming in. So my temperature delta from the front to the back of the server is off. So those heat variations, now we have throttling. Oh, I see that you're not managing the temperature very well. I'll proactively reduce my frequency in order to stay healthy until you can get me some cold air. So that's, but a CPU can fail to throttle correctly if you push it too fast, too hard, too quickly, and that frequency can't come down fast enough, or if the temperature is rising very quickly. If you've ever been in a data center that the AC goes out and you don't proactively start moving the workloads off of those servers in a hot room, you only have a couple of minutes potentially before that thing can get really hot, especially if the transformer is sitting right in the room. And that's a model. I would never do that, but The other thing to think about is over time, this idea, we look at number of hits per second over time. There's also n number of minutes or n number of seconds at temperature X for the long-term stability. So if you, again, there's temperature variation and you've got the pins and a CPU with the pins, it's a teeny weeny amount, micrometers, it's expanding and contracting and expanding, contracting. If you expand and it actually is putting pressure on something, it can eventually give out if the components surrounding that processor are cheap, right? The mount itself, depending on the motherboard, can be cheap. So why is a server so expensive? Because they spend more money on something that's going to raise in temperature and hold that temperature running at 99% CPU or more for months or years. It's an interesting way. So you can think about this as I only have n number of minutes at temperature X for long-term instability. That's how you would observe that. And then, of course, just generally, if you construct something and you don't use all of the proper thermal paste, if you've ever built your own PC, you're just not transferring heat from one substrate to another substrate efficiently. And so that's an improper installation thing. The observations you will see from really the top down, from my experience, is oddly for really long-term CPU-specific load. And this is I use tests like the TPC benchmarks from a very high level can be very good, especially if it's a very consistent and repeatable workload. But I've even done lower level stuff. If you've ever done like the disk, just check my disk, just check the memory, those kinds of component specific tests. So, but you'll see throughput degrades I've actually seen temperature slowly raise over a 24-hour, 48-hour period. Did a lot of weekend load testing where you fire something up on Friday and then check it on Monday and see what the graph said. That's how I melted that Sun server. So that degrading, you can see, wow, nothing else changed. Temperature came up and the throughput came down about 2.5%. Didn't change anything else, but when I opened the door and allowed some more ventilation to come into that room, and I saw the temperature go back down, no throttling warnings, nothing like proactively happening to throttle. Fans were running 100%. This thing is running at full speed, everything. There's still a little bit of thermal change, throughput change at that piece. And that was measured by processor schedule as well. The other thing you'll notice is that the application is just having a bad day. And I see this from a cloud perspective. It's like, well, it's just bad weather in the internet, clouds, weather, it's a nice metaphor. So, Azure's having a bad day. Well, they don't have feelings. Computers don't have feelings. It's running on a container or a set of blades within a container, and that particular thing is like, oh, we're starting to get a couple of alerts. Let's move that over to this other container. Well, you know what? We've got to turn this in. Moving it over there, that disrupts your application. Well, now you're moved over there. There's going to be a little extra latency. Then you're running on a container that's now potentially hotter than it was before. It's running extra stuff. So everything runs a little bit slower, but they're like, well, it's only for a little while, and then we'll fix this up and move the load back over. So that's like the guy down the street in the garage moving hardware loads around, moving all your workloads around in the middle of whatever you're doing. And sometimes it's like for an entire day, we took that container offline. But when it was done, we put you back in that container. And I just like, wow, why is this? What kind of a CPU fault am I seeing in this kind of stuff? But underneath the covers, we're looking at heat-related changes. And this happens a lot more in the summer, if you believe it or not, in the summer in any warm location. Clearly, the other thing we see, and this is related to heat, but also specific to power, we talked about voltage slumps, we talked about voltage surges, right? And so a voltage slump just disrupts that consistent power. The phrase of brownout I used. And that's the idea. It's not a full blackout, meaning like all the lights turn off, but it's a brownout, meaning you've got just a little less voltage. And so you maybe drain capacitors that were used as buffers to keep consistent voltage. And all of a sudden you're like, whoa, I've got to fill up. I've got to compensate for the reduced incoming current and make sure that I have enough to keep things consistent. And so those capacitors start to drain. Well, then when the power comes back, you got to fill those capacitors up. that's actually getting capacitor exercise. So that's an interesting piece. That buffer from a CPU circuit, if you've ever blown a capacitor on a motherboard, this is just a simple way. They're like, to me, they're just batteries, right? They're just a funky circuit battery. Exercising those, usually they reach a main point, consistent power. Capacitors are almost always at 100% full, ready to do their job, to make up for slumps or brownouts. A voltage surge, if you don't have a surge protector in your house, a surge protector on your power, UPS, whatever, sometimes after power is restored, it's very unstable because all the different components within the system start to kick back a little bit, suck a little too much here, give too much there, that kind of stuff. So that can blow out a capacitor, meaning you've got a surge in power. So you want to have another capacitor that's almost always empty so that if you have a surge, you can fill that capacitor as a buffer and then over time slowly drain that capacitor so that it can protect against increased power. So that's that return to full voltage that can be unstable from the source itself. So one of the things I see, if you've got a motherboard that has a slightly damaged capacitor, is that we went through some brownout stuff. We're rerunning the exact same test, but one of the servers is just like 10% slower than it was before. And you go check stuff. Oddly, there's a human thing. I wish I had the nose sense of a dog. You could smell all the stuff that's in there. It's fantastic. So slower than before. For some odd reason, and then start getting out the micrometer, millimeter, and start looking at each component. See, sure enough, one of those capacitors in the array isn't doing the full work that it would do, and it's sort of constantly keeping the CPU a little bit delayed, and that's one interesting thing you can see. The other thing to keep in mind is the CPU controls, in at least Intel architectures, but the equivalent of what would be a front side bus. And so you've got memory operations for the most part and throughput. So if you got lots of memory operations per second, and it's unrelated to size per se from a block, if you think of it as blocks. But thinking of that memory operations a second and throughput is really interesting that if the CPU is unstable, that front side bus is, at least in that, very directly connected to the performance of the CPU. So you're going to see memory operations and throughput degrade as well. Individual memory operations. But how do you handle CPU faults? You shout at the server very loudly. Really, you do what you can, right? So you can, with a CPU, like the thermal paste and whatever, reinstall the CPU, check the UPS. So if you got some battery issues or any alarms or something, if UPS is not healthy and you're not getting clean power or voltage. The other thing I'll say is check the fans. There are fans that you want to measure the speed. Maybe they're not running fully optimally. I look for micro monitoring to some extent. So if there's like less than a 1% change over a long interval of time on a clean workload, if you're doing hardware specific testing and your workloads are really clean, there can be stuff that it's a 1% difference and it's like, if you take two servers to swap the CPUs, sure enough, that one's now the slow one, that's the fast one. The only thing we swapped was this one doesn't work well on that, and it's an interesting thing. It's less perfect than we might imagine logically. It is. You can conduct an isolated benchmark, so not quite like a TPC, but you can do a controlled workload for a specific component, particularly CPU doing computation, floating point computation. You're doing aggregations of some kind. So anything that saturates the incoming pipelines for instructions and keep that CPU at a very specific workload, just one hair less than its actually intended capacity, and then see how the thermals work out, see how that works out. If you keep an eye on provider status, if there are power issues, a lot of things, if you've got power instability, one of the most delicate pieces within the system will be those capacitor rings that surround the CPU processors themselves. Memory faults. I almost forgot about memory faults. No, I'm kidding. Memory faults also, they can get too hot, right? Like any of these components. And because they're so connected frequency-wise to how the processor works, and you'll notice in a lot of server systems, it's the memory modules and then the CPU modules, and they're pulling that heat right in there. because you need some cooling of the memory DIMMs, and that's still cool enough air to go through the CPUs. That's one design piece. But with increased resistance, again, increased throughput, so increased operations per nanosecond, gives you increased resistance. So the more memory operations per second you do, the hotter it gets. And again, if the substrate within the DIMM in those ICs are not the best coming off the line, you can actually measure them if you get the infrared monitor. But you can even feel it's like, wow, that one's totally hot. That one's not. Why? They're doing the exact same work. Really interesting. Obviously, if you've got variation in temperature, so things get hot and cold, expansion, if you've ever put a DIMM in a server, those contacts are pretty, I call them lazy, but they're pretty just physical connected. They're just connected in there, and they're made of metal, so they will expand and contract, and there's plastic around the metal, expand and contract, and if that gets too hot, it'll actually melt the plastic before it So considering cheap memory, it can't take the heat as well as more expensive means, simply because there's less resistance within the component itself. Again, one weird thing that I found, and it's not often, but you'll have like paging operations, pages of memory happening in a DIMM where it's getting like flushed out to disk. And maybe a database operation working within a shard. Maybe you've got something that's coming out of memory, but it's going to be stored on disk. And on its path of moving through memory or coming out of memory, there's a known working sector. It's not a bad disk, but there's corrupted data on its movement off of memory and flushed to disk. And so you could actually see corrupted blocks of information where the DIMM is working well enough to do the memory operation, but if you do something that's as fast as possible trying to get it to disk, and now you've got SSDs, it exacerbates it. You got an SSD with a bad sector, cheap SSDs, that's an issue. We'll talk about that. The other thing is, memory is required for any computer to run for the most part. Unexpected operating system restart. Hey, even the memories of the operating system is using up memory, and all of a sudden hits a bad DIMM, hits a bad IC on a DIMM, done. It gives up, blue screens, whatever. And so if you have contiguous memory access, the paging piece where it's contiguously increasing memory. So I'll do something where I start with an application workload very low and then slowly increase that over time. Oddly, depending on how it's allocating that memory across all the DIMMs, all of a sudden you hit a bad DIMM and you'll see what address it is. You're done. If you hook up a debugger to the operating system, you can even get in and actually figure out what. Sometimes we figured out exactly, hey, what block were we looking to try to get data out of? The other thing is memory modules have voltage requirements as well. They operate off the front side bus frequency. So, but more simplistically, if you've ever taken DIMMs out and then like you lick them or you rub your hands, put them in your hair, static electricity will mess up memory. Those contacts, if you're making electrical conducting between those. So don't do that. But again, somebody says, oh, we upgraded the hardware in the server, we put new memory in. It's like, well, that was some clumsy person who had, coffee in one hand. Here, I got my coffee and I got my DIMM, and I just put the DIMM, store my coffee with my DIMM and then put it in the server. These things are very sensitive, right? You don't want to do that. But also the same things that affect the CPU. So over voltages, surges, there are buffers and capacitors even on the DIMMs themselves, depending on the manufacturer. The other thing is there's a lot of rules about mismatching DIMMs, different frequencies and different qualities, and they talk to each other differently, so to speak. They also consume power differently, which means within the different banks of DIMMs, you want to have them matched because usually they're paired up from a power perspective to make sure those banks are uniform and you're flowing the current evenly between both instead of favoring one and burning out or stressing one capacitor or one buffer system over here for current versus another. So that's why you want to have matched memory, even if it's all cheap. Unexpected OS restarts, again, the daily load increases. So if you're looking at power issues and there's power issues, potentially you're at max power on a circuit or something like that, if you come up to that same usage every day and suddenly you're, pushing that, I would look at CPU and memory. And then, of course, memory is something that usually does get checked. You can enable it as servers or most systems to do a full memory check. Doesn't happen that often, frequently, but you can if you do hardware upgrades to the server and then suddenly it doesn't boot, or it comes up and boots, but it doesn't boot the operating system. That's an indication that potentially that's bad memory or something like that. How do you handle it? Obviously, go in and shout loudly at the computer. Same kinds of things, reseating, reinstalling the components, memory DIMMs, make sure, take them out, put them back in. Checking the system fans. Again, if you have dedicated cooling for the DIMMs themselves, make sure that that's not leaking. If it's liquid or that kind of stuff, make sure you get that all working at peace. And then do that memory check at the OS startup. Bring it down, do a full memory check, and then that used to be a common thing on almost every computer. I always measure the private bytes usage, particularly when doing an increasing consumption of those private bytes, because you're taking on more and more of the individual sectors in the DIMMs. And you'll hit a bad one. You'll hit a bad IC within that chip itself. So gradually increasing load test specific to memory. And then in the cloud, again, you just check that provider status for power issues. I'm moving along in time. We usually do QA, but I was playing guitar, so I'm going to try to get this moving. We'll come right along, Henrik. Let's talk about disks. And disks and storage. I think about disks as good old spinning disks, but also SSDs, and then storage. SANs are a different thing. So let's talk about physical disks first. Obviously, spinning disks in the old days, you didn't take your laptop and bang it on the table because there's a record player in there. I don't know if you know that, but there's little needles and stuff, and one will get stuck and bent, and that kind of stuff. They'll break off. Obviously, the platters in there are completely delicate, and they do all they can to keep those things from flopping around like that. But they can be damaged and impact. Majority now, we're dealing with SSDs. And the real thing with SSDs, again, because they're an electronic memory component, if you've got cheaper materials with higher resistance, you're going to have more heat. So again, if you've got heat concerns in where you're running, looking at higher quality components, you got to figure out the dollar per, is it the cost benefit analysis to figure out that's it. So even in smaller servers, if you're going with cheap SSDs or an NVE RAM kind of stuff, even you've still got higher the throughput, lots of current going in and off the thing. There's also SSDs, keep in mind that that's really a memory. There's also controller units for SATA or like in the HP world back in the day, it was SAS drives, the SAS interfaces, and they started going to solid state. There's still controller components. There's microprocessors that are sort of governing each of the banks within the multiple banks that are in the SSD. But heat is definitely a consideration. Those on-disk controllers also have voltage issues, which is why you see dedicated power in a section just to power the hard drives. The nice thing about SATA is you still have SATA and power, and so you're really talking directly, not coming off the motherboard, you're talking directly from the power supply with sort of dedicated linkage into their buffers, which is nice. Your disks that are inside the server, not necessarily on an array or something sitting outside, obviously you're sharing the cooling of the design of the box. So where those disks are and looking at shared airflow, that's another consideration in terms of making sure you've got enough dedicated air going to memory and CPU, but also some air that was going. This is a bigger deal with higher temperatures coming off of 10,000 RPM drives and that kind of stuff. So yeah. Here's the thing that I look for if a disk is going to fail for me for these reasons. One, a sequential I/O pattern of some kind, sequential reads or sequential writes will either just outright fail to write, cannot write to disk, that kind of stuff. Or there's an OS level exception and it retries somewhere within the driver mechanism. But you can look in the OS to say you get warnings and that kind of stuff. They'll come out and say message warnings or something like that. The other weird thing that I've seen, especially with cheap memory, cheap disks, is doing defrags and optimizations it doesn't really burn them out, but you're constantly defragging stuff to keep it in a certain way. And then those hotspots just get hammered over and over again. stuff wears out, and mostly it's because it gets hot. It expands and contracts, or it'll eventually melt something if you don't do it right. Storage SANs, really big storage SANs, they're really just big computers, right? And they fail for various reasons as well, but they're really big computers with very, very small purposes. Like all I do is IO request in, IO request out, have a nice day. I don't really do anything other than that as a SAN. But there's dedicated ASICs. Once we get into storage, any of these IO pieces, we don't have to know how to run solitaire or your email. We just do IO. So the ASICs is a very specific chip, and the more throughput we want, we can start putting as many ASICs as we can inside the box, so we have dedicated paths to do all that logic, right? And if you're calculating RAID, if you're calculating the patchwork layout across a SAN, all of that computation is sort of routing I/O within the controller system, and they're really just an array of microprocessors. Guess what? Those are CPUs, and all of the rules apply: voltage, under voltage, over voltage, power, and then of course heat, cooling. So the thing is with these guys, usually SAN storage is really expensive when you break it, which is why you see they sort of overcool things. They really take care of the power because these things are so specific that when they do their work, they can be incredibly controlled. Because they're so specific in a workload, you can control what they do. So look for transient volumes, latency blocking, or missing disk, like missing disk, and then the disk is there, but the missing disk, but the disk is there. And so you've got a message kind of going back and forth between something that's sort of there and not there, or something's not connected right. There's something within also like fabric connections and interconnects that you could see for storage, where much like network we'll talk about, it could be just physical networking pieces. The other thing I'll say is monitoring the temperature of the ASICs themselves, right? So overuse, and some of the really advanced SANs, their individual controller, the blades that they have for controllers with the ASIC chips on there, they have thermal warnings and stuff internally. You can see whether you're overheating. You got too many IO requests going through one bank, spread those connections out onto different physical connections to do that. And if you have a really smart fabric, it'll do it for you. And then, of course, transient RAID errors. So inability to synchronize RAID doesn't happen all the time. Every now and then, well, why is that happening? It can be related to some kind of a block level fault, a sector level fault, or caused by damage. Again, shout at the server. To what you can do, much like memory, do those disk checks and do a block level copy and move. Take an entire chunk and copy it to another sector and see if the same thing happens on a different disk or a different sector of the same disk. Take your MDF files, make a copy of the MDF files, rename those, remount them, and run the same test. Well, then it is maybe something to do with where it was on the disk. And you can look at certain disks being hotter than others. If they get hit, hotter meaning they get hit more than others, and see if there's ones within a RAID. Wow, that LUNs group really gets hit a lot. Let's spread that out across the controllers and across more disks. The other thing is, with the way they do RAIDs and quilted patterns and things like that, it increases the tolerance, but it can also change that. A few more thoughts here. Design layouts to avoid the SAN doing automatic movements, because that's disruptive and causes latency. So if you can avoid automatic relocation of storage virtualization, do it for your really good stuff. Just say, well, we know where that's going to run, and we'll set it up and run it that way. I like doing massive load testing for reads and write workloads. Again, sequential reads and sequential writes in databases, and do really long running tests to do this. And yeah, the other thing to handle IO writes, obviously in different infrastructures, it's we're handling stuff that can retry things. And so do that. Make sure your application can actually retry something if it didn't get to disk. I'll wrap up with network. Henrik, we're right on about midnight, so I'm going to keep going. Is that all right? Network components, they can fail to do heat. The observations for this are you've got similar kind of thermal computers. A network switch and a router is actually a computer. So there's two really interesting things. If I go to the second page here, the other reasons that networking components can fail that I've observed are the dumb ones, right? So if somebody puts something in with, you got power over Ethernet, and it just destroys the component, and in so doing, maybe even destroys the power component within the switch itself. The other thing is overuse. So somebody finally looked at me and said, hey, you know, like in this switch, there's like 4 little bundles of ports. And I'm like, yeah, that's great. And it's like, well, open the box. So I opened the box, and guess what? There's one bundle has 2 microprocessors. Bundle has 2. So each one has 2 micro. So the top and the bottom have 2 different ASICs, and the top and the. But I had all of my high throughput stuff thinking in my brain, oh, I want them as close as possible together. So I want them to be on the same thing to reduce latency. And I was actually overloading those processors in that bundle. And they're like, well, just take every other 2 across that switch. Take your hot ports and move them across the switch. Totally interesting thing. Suddenly, all the processors are working, no thermal throttling. The back plane on that switch, that router, was really fast. But the physical things you'll see with network are really interesting. So disconnecting, reconnecting cables, jiggle the handle, checking for errors, link errors, and that kind of stuff. Again, moving those ports around the rack to spread out the hot links that are actually on there and make sure they're spread out across the ASICs. And then, of course, you can always just try moving workloads and containers onto different hosts. And, of course, those hosts are on different network connections, and see if that helps and you can track something being hot. Same things you would normally measure when network switches start to throttle or start to fail. Obviously, within the ANSI spec and for TCP/IP stuff, it's retries, packet failures start to increase. If you can monitor it, monitor the internal temp CPU. It's a computer. A switch and a router is just a computer. So, in summary, I'm going to bring this home within a few minutes, but we could go on. Always shout at the server. That's my summary, but it won't really help anything, but it'll make you feel better. Hardware is failing around us all the time. You know it's happening. The majority of the time, you don't even know it's happening. It is handled very, very well. And a lot of the times, but those unexplained, I don't know why it's 5% slower today. It could be hardware. The cloud is not fault-free, but we're doing an amazingly good job of keeping it fault-free with all of the compensations we do in large clusters, right? And on is great, but on and great, fast, cheap, cool, mostly fast. Just because something is on doesn't mean it's good. Your 5 nines mean nothing if users aren't happy, right? So specific tips: increase the detail and granularity of your measurements. So some of these variations, we're looking 1 to 2% difference on a very consistent workload over time. Improve your ability to compare results and measurements over time. Here's yesterday at the exact same workload, today at the exact same workload. Using canary load, I fired up a server and I have some canary VMs that are just doing very consistent workloads, not our production workload. And we're just seeing, for some reason, power is different and cooling is different today. While it's 3 degrees warmer outside. Okay. Wow, there's a sunspot. That's weird. There's a voltage spike. And then get into that designing of specific benchmarks to test specific hardware. Here's a 3-way hash aggregation on a couple billion rows. Well, that's going to definitely hammer a CPU or an array of CPUs for a good long, 3-4 hours. And there you go. So now you got a very consistent, repeatable benchmark to put any CPU under that workload. And that's where I'll wrap it up. We'll let it go. Thank you guys very much. It's always a pleasure to be with the pack.